All right, guys, Mr. Antonucci here, and in this video, we're going to talk about area between the graphs, particularly how to find the area between the graphs of two functions with respect to the x-axis. So if we look at a general region here that's bounded by two functions, f and g, we can figure out how to get the area by the same way that we figured out the area under the curve by basically doing a representative rectangle and getting the area of that and then going from there. So if we draw a vertical rectangle here between the two functions like this, okay, the area of that rectangle is the height of it times the base of it. The base of that rectangle is the width of the interval on the x-axis. So what delta x is. The height is actually the difference in y values. So you can think of it as y2 minus y1. Okay. Well, y2 is the specific y value at that point for f of x. So that's f of x minus the specific y value for the g function, so g of x. All right, so we have f of x minus g of x gives us the height, and then times delta x. Well, that's just for an arbitrary vertical strip. If you could imagine, you would have to pack in multiple strips and then get the areas and add them all up. So what ends up happening is we end up having a Riemann sum from I equals 1 to n. And then if we take the limit as n approaches infinity, we would get the exact area under the curve. Well, this should look very familiar for whenever we figured out area under the curve. This would give us the area between the two curves. So here's the formula, because this, when you take the limit of a Riemann sum, it's the same as a definite integral in this case. So the area of the region bounded by two graphs is the definite integral from a to b of f of x minus g of x. And I always like to tell students top minus bottom, okay? Because that helps us figure it out very easily. Now, this formula is going to work no matter where the region is. Notice the region in our example, the part of the region was below the x-axis, but that doesn't matter because the subtraction makes it all work out. You're still getting the difference between the top boundary and the bottom boundary. So it doesn't matter if it's in the first, second, third, fourth quadrant, or over all of them. So let's look at an example here. We want to find the area of a region bounded by the graph of e to the x and square root of x and the lines x equals 0 and 1. First thing you want to do is graph it. I already have it here, and then figure out where the region is. So x equals 0 would be from here to x equals 1, which would be right here. So you end up, I'm just going to shade in there with that region right there. And so we want to figure out the area of it. So to get the area, we need the integral from 0 to 1 of the top function. Well, this function right here is obviously the bottom function, so that's square root x or g of x. And then this is the top function, which is f of x. So if we go top minus bottom, we would have e to the x minus square root x dx. We could anti-differentiate those. That'd be e to the x minus x to the 3/2 times 2/3, plugging in 1 and 0 and subtracting. So if you plug in 1, you would have e minus 2/3. And if you plug in 0, you would have minus 1. So this is going to be e minus 5/3. Now we could check this answer and get the approximate decimal value by using Desmos. So I have e to the x here, gx here. And now to get the area, we can call it a. A equals the integral from 0 to 1 of f of x minus g of x dx. Now we have a warning here because we have to put parentheses around the integrand because you got a lot of different stuff going on there and it's confusing it. So here we go. Yeah, we're going to just have to take that off there, right there. And I see an equal sign there accidentally, so we get this. So that's 1.0516 and some change. And then if we compare the answer that we got previously, which was E minus 5/3, see we get the same thing there. Pretty cool, huh? Next example, want to find the area of the region bounded by the graphs of F and G here. Now, one of the things that's important to note with this one is that they did not give you the limits of integration, so you actually have to find those. So what we have to do is set the equations equal to each other. You get f of x equals g of x. Okay, so in this case, we can actually do it. So you have 10x minus x squared equals 3x minus 8. You set that equal to 0, you'd have x squared minus 7x minus 8 equals 0. We could factor into x plus 1 times x minus 8, and then you would have x equals -1, x equals 8. So if this was a free response question, I would have to show the setup of the equation and the limits of integration here if they don't explicitly give them to you. Okay, then the integral, or the area, is equal to the integral from -1 to 8 of the top function, which is going to be the parabola f of x minus g of x dx. So this would be the integral -1 to 8 of 10x minus x squared minus 3x minus 8. And you could simplify that by distributing the negative and combining the like terms. Whoops, move the screen there. But we're going to actually evaluate this using Desmos. So there are two functions graphed here. You can't really see it. If you hit, you could actually zoom out a little bit, and then you can see where the region lies. Also, because we have Desmos here, we can click on the intersection point and put it in um, our table of functions over here. And then this could get you your limits. But again, you have to show the equation that you're solving here on your work. So you would set f of x equal to g of x, and then you could write x equals -1 and 8. To get the area between those two, you would do our integral from -1 to 8 of f of x minus g of x. And again, it's not always going to be f minus g, it's top minus bottom. So in this example, in the previous one, they were both f was the top function for both of them. So you'd have 121.5. And if there was a context, it'd be the units squared or square units for whatever it is. So let's go ahead and look at another example. So here we want to find the area of the region bounded by the graphs of sine and cosine from 0 to pi. So this one's a little bit tricky here because we're going from 0 to pi, which is from here to here. And you have to get the region that is trapped between the graphs. So look here, and then the other region would be right here. The problem is that at this point where the two graphs intersect right here, the top and bottom switch. So what we have to do is split the integral up into two separate pieces, one where the cosine function is the top and the one where the sine function is the top. Now the green function is cosine and the blue function is sine. And you could get that easily from the y-intercept. So the area is going to be the integral from 0 to pi over 4 of cosine x minus sine x plus the integral from pi over 4 to pi of sine x minus cosine x dx. And in both cases, you'd have to get the antiderivative, plug in the upper and lower limits, and subtract, and then add your answers together for this one. But again, we can just plug this into Desmos, and you would get the answer to three or more decimal places. Now, if you're asked for the exact answer, or this is a no calculator or Desmos allowed portion, then of course you're going to have to show all the work by hand. Another way that you can actually do this one, and it's going to be a lot easier for Desmos, is thinking about what's going on here. You're getting the area of the region between the two graphs. So if you could actually do it on the whole interval from 0 to pi if you did the absolute value of sine x minus cosine x. Because here's what happens. Since sine x is on the top for this region's going to end up being counted positive. But if you do sine minus cosine for this other region, since sine is on the bottom, it's going to give you the opposite or the negative value of that region. However, if you take the absolute value, it's going to report the positive for that. And so you'll end up getting the whole entire combined area in just one integral. On Desmos here, I put the original way we wrote the expression, and you get 2.828, which in fact is 2 square roots of 2. Now, if I do the absolute value method, I set up the integral here. Absolute value, we could do sine x minus cosine x dx, and you get the same thing. And just to show you, if we had done the other way, since it's in the absolute value, minus sine x, you still get the same exact answer there. Okay? So in example 3 here, this was example 3a. 3b, we want to write the integral that gives the area of the region enclosed by these two graphs and use Desmos to find that area. So in order to do this, we need to first figure out what is the top and what is the bottom functions and their intersection points. So first thing I'm going to write down is f of x equals g of x. Since f and g were already defined in the problem, I can write that, and that means I'm going to solve for the intersection points. So I'm going to hop over to Desmos now. So I have my two functions graphed here. Now I'm going to record the intersection points on my table of values here. Okay. And then I'm going to let a equal 1 negative 3.0756, and I'm going to have b equal 1.40894. Then I can get the integral from a to b of, now notice the line is on top here, so g of x minus f of x dx, and it gives you the answer here. The reason I like doing it this way is I'm not copying these two numbers for the limits, and then I can just use A and B from that point forward, especially on free response questions where you might have to use these values again. Now, I want to go back to the actual problem and show you what you would need to write on the problem in order to get credit. So here we go. F of x equals g of x, and we found that x equals 1.40894, and we called that B, and x equaled negative 3.0756, and we called that A. Then the area is equal to the integral from A to B of g of x minus f of x. All right, since f and g and a and b were already defined, I can just use those instead of writing out the entire functions and numbers again. And then I could just put the answer, 15.0315, go out at least 3 decimal places of accuracy there. Okay, and then that's all I would have to do. All right, so this brings up the question, what if g of x is non-positive on the interval? In other words, what if it's just strictly negative or 0 on that interval? So for example, if you had the graph of a function and it was all down here, this is g of x, and I wanted to get the area of this region. Well, actually, the area from, let's say, here to here, A to B, the top boundary is actually the line y equals 0, and then the bottom boundary would be g of x dx. So that's equal to negative integral from a to b of g of x dx. Okay, so this logically kind of makes sense. All right, so if we're trying to get the area of the region, and the whole region is just below the x-axis, the whole function, right? If you just did the regular integral, it would give you a negative value because the region was below the x-axis. But if we want the area of that region, then you would have to think of it as top minus bottom. The top is the line y equals 0, and the bottom is the function. Or that's just the opposite of the definite integral of g of x. So have another example here. We want to find the area between a graph in the x-axis. So we have x squared minus 4, the x-axis, and the lines x equals 0 and 5. So the region, again, is defined as what is trapped between the x-axis and the function. So from here to here. So this is kind of why I brought up that whole thing about part of the region being below the x-axis. Because for this one, if I want to go from 0 to 5, notice that part of it is below the x-axis and the other part is above. So that first part is actually bounded by, from 0 to 2, is actually bounded by the x-axis, which is y equals 0, and f of x. And then the next region is 2 to 5 of just f of x. Okay, so this could simplify to negative integral 0 to 2 of f of x dx plus integral from 2 to 5 of f of x dx. All right, and so if you took the antiderivatives, you would get, for this first one, you would get 16 thirds, and the next one you would get 81 thirds, and then it would be 32.333 repeating square units. Now, if you are allowed to use Desmos, there is a easier way to do this involving absolute value that I hinted at before when I showed you an absolute value one. So I'll bring over Desmos and show you how to do that. So here we have the function f of x equals x squared minus 4. If we do the integral from 0 to 5, we would want to take the absolute value of f of x, and you get 32.333 repeating. Because the absolute value, essentially, if you look at the absolute value of f of x, it's essentially going to swing or reflect anything that's negative over the x-axis and make it positive. So if I'm taking the integral of that, it's going to count this region as positive, and then the region from 2 to 5 is positive as well. So then you would get the full correct answer in one fell swoop. And that's it for this piece. I hope that was helpful to you. Reach out if you have any questions, and take care.